Good, eve- Good evening, everyone. It's already 6. We'll wait for another 5 more minutes for others to join the class. Then we'll start. So good evening, everyone. We'll start today's lecture. I'll just share my screen. Can anybody confirm if they are able to see the screen? Okay, thank you. Yeah. So today we'll start with the lecture number 4. In the previous lectures from last 3 weeks, we have been studying the optical microscopy, where we have studied different optical microscopy techniques and the sample preparations. Someone is in the lobby. Let me admit them. Okay. Yeah, so we have till now we have studied all the optical microscopy, the sample preparation, and the professor has also given the demos of every optical microscopy technique which have been used, the sample preparation and everything in the videos as well as in the lectures, and we have covered their quizzes and practice assignments as well. So from today we'll study the scanning electron microscopy, which in general is known as SEM. So this is lecture number 4 for this material characterization course given by Professor S. Sankaran from IIT Madras. And here am I, Dorothy Sachdeva. I am the PMRF TA of this course. I am a PhD research scholar at MRC department at ISC. So today we will study firstly the introduction to the scanning electron microscopy and then the lens aberrations. We have already studied these lens aberrations in the optical microscopy and the same we will study in the SEM mode. Someone is in the lobby. Let me enpin them. Then we'll study the lens aberrations and then followed by the parameters which will govern the formation of the image in this SEM technique, the interaction of the sample with the electron beam which are coming vertically downwards, and the elastic and the inelastic scattering which is happening in the sample specimen itself, followed by the role of the secondary electrons and the back secondary electrons which are emitted from the specimen, and what is the role of this working distance in the condenser lens and how these things affect the image formation in the SEM. Followed by we'll do the practice assignment and the quiz as usual. So firstly, what these SEM uses electron as the incident beam which is used for the imaging purpose. So as we studied in the optical microscopy, the Snell's law is followed. So in this case also this Snell's law is followed, and the refractive index which was used in the optics in the optical microscope, here it corresponds to the field strengths. So sin r by sin I is given by the under root of v1 by v2. So just the refractive index is given by these field strengths. Here the electron beam will undergo this refraction. The lenses here are not some physical lenses. Like in the optical microscope, we use the convex and concave lenses which are made up of glass material. But here we use the electromagnetic lenses. These electromagnetic lenses passes the electric and magnetic field within themselves, and those electric field converges the beam of the electron so that it can fall on the specimen. So here the lenses used are unipotential electron lens, where the object and the image are at the same potential, that is at the same refractive index. Since the potential of the electron beam from the specimen and the image will be same, so they both the object and the image lies in the same refractive index, that is the same potential. So that's why it is known as the unipotential electron lens. Here the in electron microscopes, the when the electron in, I'll just use the pointer pen. In optical microscopy, we used this as the optic axis and studied that the rays are coming along this direction and are getting focused or converged or diverged depending upon the type of lens used. It will get converged or diverge like this. But in this scanning electron microscopy, it is the vertical. Here the optical axis is the vertical axis where the lenses are present here and the electron beam travels this path, vertical one. Someone is in the lobby. Let me admit them. Yeah. So here the all the optics is being studied in vertical direction. And also there is one thing which you need to keep in mind, that in the optical microscopy we studied the magnification M as well as the demagnification D. Generally in the optical microscopy we used to magnify the object. We just wanted to see the object in a higher mag, the more closer to look at the object. But in this case, the SEM, there is no direct correlation of the object and the image using this ray diagram. Just keep this in mind. There is no direct correlation of the object to the image using this ray diagram. In optical, we used to draw the ray diagram where this was our object and this is the optic axis, and if this is the lens, depending upon the distance the object is placed and depending upon the lens used, we'll get certain formation of the image, inverted image in this case. So here we can directly relate the object to the image using these rays. But in this SEM, we can't directly relate the image to the object using the ray diagram. Here the ray diagram in the SEM is used only for the probe thing. Like we have a specimen and a probe falls on the specimen along vertical direction, and this probe, our main aim is to converge this probe, to have this probe falling on the specimen. So if this, so the optics here used is to converge this electron probe. It won't tell you directly the image correlation with the object. Here when the electron beam is coming in this vertical direction, and these are the your pole pieces which gives you the magnetic field, electric and magnetic field. So when the magnetic field, so when the electron is falling vertically in this direction, and due to this magnetic field it experiences force which is perpendicular to this. So if the electron is moving vertically downwards in this direction, which I am showing now, and there is a magnetic field in this direction and is in this direction, this is the longitudinal and this is the radial part of the magnetic field. Then according to this, when the electron is coming down, then this radial part will contribute to the movement of electron. So by the contribution of this velocity longitudinal of electron and the BR, that is the radial component which is perpendicular to this optic axis. So the combination of these two will result. So if the electron was coming like this, then due to this radial component, it will move slightly away from optic axis, and from the other direction also the same thing is being there. Now if the electron is moving in this direction, which I am showing right now here, if the electron started moving in this direction, then the longitudinal component, that is this component BL, this one, this will force this electron to go to backward direction perpendicular to these both. So the combination of this longitudinal and the radial components of these with the velocity of electron results in the spiral motion of the electron. So electron follows this spiral kind of motion in this magnetic field. Did you got this point? Firstly, the radial component will contribute to the movement of this electron and followed by the longitudinal component. These both things will then result in the spiral path of the electron. Is this thing clear to everyone, or do you have any doubt? If not, then we'll move forward. So these are the early SEMs, which are this is the first modern scanning electron microscope, which was constructed by D. McMullen in 1951. And this is the on the right hand side you are seeing is the first commercial SEM which was being used. So in SEM, we'll first discuss, so what are the basics of this SEM. Firstly, there is the electron gun, the source of the electron gun, from where the beam comes. It has different types: the thermionic field emission, the Schottky field emission, the field emission, and all. And after that, a lot of electron beam is produced from the signal. Then our main aim using the electromagnetic lenses is to have the fine probe. That means to produce a tight spot on the specimen surface using these condenser and the objective lenses. The condenser and objective lenses, the naming of these lenses are based upon the position in which the lenses is being placed in the SEM. Then we have these scanning coils, the raster. What does this raster mean? Can anybody explain? That in SEM we always do the raster scanning. If this is your specimen, then in SEM your whole image will not come at once. It is scanning electron microscope. So here the scanning is done like this, from point A to point B, and then from point A1 to point B1, followed by this A and B series. So the probe will go from A. Can I choose another color to show? Yeah. So the probe will go from A position to B, it will do a scan, then it won't do a scan, it will come back, and then it will start the scanning again from point A1 to point B1. Then it won't do scan, it will come back and do the scanning from point A2 to B2, and then it won't scan, it will come to point A3 to B3. So this is not dragging back, it is a continuous scan. So this is known as the raster scanning. So here the scanning coils do the raster scanning, and the size of scan will depend upon the will tell about the magnification of the image you are getting. And then we have the electron specimen interaction, which produces a very huge variety of signal, and depending upon the detector which you are using, you will get the information. If the electron beam is like this and it is interacting with your specimen, then it will produce all kind of signals. You can't restrict the type of signal which it should produce, but you can have a detector which will detect only a specific type of electron, so that you can get the information according to your requirement. So it will always produce a variety of signals, but depending upon your requirement, you will have a detector such that uh, it will attract only the electrons which are required for your information. Then we have the detectors which will collect the signal from the specimen, and the different detectors are used for the different kind of signals. Then this is the basic of the SEM microscope, where initially I'll take the red color only. Yeah. If you have any doubt in between, you can just raise your hand. I'll ask. So in SEM, firstly, I have told you that it is the vertical optics. It is not a horizontal one. So you have your specimen over here, and your optical axis is this one, which I will be drawing right now using my red pen. So this is your optic axis. So firstly we have this electron gun. Electron gun produces the electron by heating or by thermionic emissions or by field emission, Schottky emission. There are different sources for the electron gun. Then this electron gun produces the electrons, which then passes through this anode. This anode is negatively charged, so it repels the electron, so the electron converges and it passes through the anode. So then followed by this anode, we have this condenser lenses like here, and the objective lens. This is also a condenser lens. There could be multiple condenser lenses, but the objective lens is always the one which is just above the specimen. Just keep this in mind. You can have multiple condenser lenses, but the objective lens will be only one, which will be the lens just above the specimen. Then this electron beam will pass from the condenser lenses followed to the objective lens, and then it will pass through the specimen, and after the interaction, then this electron beam will interact with this specimen, and different kind of signals will evolve out from this specimen, where you can have different kind of detectors. Like they have X-ray detector over this, shown in the black one, this one, followed by they have this secondary electron detector, and also they have shown this back secondary electron detector. This back secondary electron detector is something of like the donut shaped. I'll just remove this thing so that you can see it more clearly. This back secondary electron detector is a donut shaped detector which is placed just above the specimen, where you can collect the back secondary electrons. And later on we'll study what this secondary electron and this back secondary electron means, and how are these signal used for the further information. This thing is maintained under a very low vacuum condition. This all the chamber and all the gun part, this is the gun part, this is all the chamber part, so this is the sample chamber, and this is the all this is under very high vacuum condition. This is the basic of scanning electron microscopy. You always need to know, firstly we have the electron gun source, there could be different kinds, followed by the condenser lenses and the objective lenses, and then the specimen, and then there will be different kind of detectors. Here it will do scanning, so the electrons will reflect back, and depending upon the detector they will take, this will take different kind of electrons, this secondary electron, this backscattered electron will take different kind of electrons, this X-ray detector will take different kind of electrons, and they will give information according to the collected electrons. This is the basic. So is this thing clear to everyone? Is there any doubt? Is there any raise hand or any doubt, any comment? There isn't. So I guess everyone is clear about this basic principle of this SEM working of this SEM. Next, I'll study in detail what is this electron gun means. So this electron gun itself has various components in itself. So firstly, there is this filament which is being heated. This we are talking of the thermionic field emission. In the thermionic field emission, we have a filament like this. It is generally a pin-shaped filament like this. It is sometimes known as hairpin filament. This tip is made smaller so that if we heat it, if it is very broad and we heat it, it will take a lot of time. But if it is pinpoint, like it is known as hairpin, if it is thin enough, then if we heat it, it will produce electron much more faster as compared to the broader one. So here we pass current which should be higher than the work function of this metal. This is usually like this U-shaped or this pin-shaped one. And then if the provided energy is higher than the work function of this metal, then the electrons will get emitted from this filament, and then it will then we have these grid caps on both the sides which are connected to this bias resistor. This provides a voltage in such a way that positive voltage in such a way that electrons get attracted towards them, so they start moving this, so they diverge over here, and after this we have this anode plate which is negatively charged. So this anode plate is positively charged. This anode plate is positively charged with respect to the filament. So this anode plate will try to accelerate all the electrons which are coming at a certain electron volt energy from the grid gap distance. This grid cap is negatively charged. I need to correct myself. This grid cap is negatively charged. The negatively charged will remove the extra electrons which have been generated from the filament, and this anode plate is positively charged, which will increase the acceleration of the electrons coming from the grid cap. This is this thing clear? I need to make myself clear here that this anode plate is positive charge with respect to the filament potential, and this grid cap is the basically the electrostatic lenses with the negatively charged to remove the extra electrons and to control the number of electrons which are coming out from here. It is basically this grid cap is used to focus this. The grid cap is connected to this bias voltage, and this bias voltage can also vary with the emission current. So this hole is known as the self biased electron gun. So basically uh, then the beam will pass from the anode plate. This is known as the current which these electrons carry with themselves now is known as the beam current. So basically there are three kinds of current. One is, I'll clear the screen. Three kinds of current. One is I, E, I, B, and I, P. So basically IB is the beam current, which is the current carried by the electron which is anywhere in this chamber, and this IE is the emission current, which is the emission current which is grounded by the system, and this IP is the probe current. The probe current will be the current which will be experienced by the specimen. There is a lot of loss and gain in within the electron current of this electron during the passing from the generation up till the region where it reaches the specimen. So different, depending upon where we are looking at, we can have different values of current. So the beam current which falls on the specimen is given by the IP, which is the probe current. This is the smallest one among all these IB and IE. So these are some concepts which I would like to discuss with you people, where the current, the electron which are passing from the chamber is defined not by current, rather it is defined by the current density, or even not the current density. Later on we'll come to know that it will be defined by one term known as the brightness. So the current density of these electrons will be given. The current density is basically the amount of current the beam is carrying, or with divided by the total area. So the current density JB is given by IB divided by pi d by 2 whole square. This I already told you that the emission current will always be greater than the beam current. Emission current is the current which is grounded, and the beam current is the current carried by the electron in the chamber. So this, using this current density, we will calculate the brightness of electron at any region in the chamber. This includes the current density but also recognizes the change in the angular speed of electron as they are focused. So this current density has the current as well as the probe size, like pi d by 2 whole square. But this brightness terms includes the change in the angular speed along with the current density. So this brightness is defined as the current density per solid angle, where the solid angle is given in steradians. This is the unit for the solid angle which is generally used. Just remember this, steradians. This brightness term will tell about the how the gun is performing. Like in certain cases, the gun went bad after certain amount of time. Like when the gun is being run for a longer duration, it will get degraded, and there can be certain kind, if that I told you, no, that these are pin kind of like sources. After certain time they can either break from in between, so it will not give a good quality of signal, all, or there could be damage at the source from where the electron is being produced itself. So this brightness term can tell about the performance of the gun. This brightness is given by the symbol beta, where beta is given as current per unit area per unit solid angle. So the current density was given by IB divided by pi d by 2 whole square. So that d by 2 whole square will give pi d square by 4, and that 4 will go above, and that the solid angle is given by pi alpha square, and this angle is given in steradians. This solid angle is pi alpha square. So the current is IB, unit area is pi d square by 4, and this unit solid angle is pi alpha square. So combining these all, we will get the brightness equation in Armstrong, uh, ampere per centimeter square per steradians. So this beta unit is ampere per centimeter square per steradian, and is given by 4IB divided by pi square, d square and alpha square. Is there any doubt till now, or is it's all good? No raise hands. Okay. Like in optical microscope, we used to either magnify or demagnify. Basically, we want to see the object at a higher mag. If the object is very small, then we need to see the object much more clearer. So there we need to do the magnification of the object. But in SEM, as I told you, that image is not directly correlated to the object. Here the optics is only used for the path of the electron which it follows. Like until here, as you can see in this diagram, until here it will follow all the optics. So the optics is who is there? So up till here, all the optics is being followed by this electron. Like, so our aim is to have, if this is my specimen, our aim is to have a probe which have the pointed edge, right? So the pointed edge means that if the electron source is providing this much electron and I require a point size, this means I am demagnifying the electron probe from this much diameter to this much diameter. So that means I am demagnifying the electrons, electron probe. So in this SEM, we always used to do the demagnification of the electron probe. we always do demagnification, and demagnification will be given by the object size by image size, which will just opposite to the magnification. Magnification m is given by the image size by object size, and the demagnification is given by the object size divided by the image size. And I'll tell you what this alpha means. I guess it's written somewhere. Yeah, I'll show you afterwards what this alpha means. This alpha. So at each SEM lens, we will demagnify the source lens and we will magnify this alpha. I'll just tell you in a slide what does this alpha mean. Like I'll just zoom in. Zoom option. Magnify slide. Yeah, can you see this ray diagram? So the rays which are coming along this direction, it will get converged at this point as well as this point. So now my aim is to tell you what is this alpha. Alpha is basically, if this is your optic axis where I am keeping my hand, this, I hope you are able to see. If this is your optic axis, this one, and your ray is being focused over here, then the angle between your ray and the optic axis will be the angle alpha. I hope I can draw it so that you can visualize it much more clearer. Basically, this angle will be the convergence angle, the angle alpha. Okay. And I also wanted to tell you that what are the apertures. These apertures are basically the holes. Basically, you have a grid with certain different size of holes, and depending upon the thing, depending upon the image which you required, the information you required, you put different kind of aperture. These are basically the physical holes. Like this is all metallic, and these holes are hollow. So depending upon the information you required, you will put this different kind of aperture. So aperture basically is a spherical thing which will restrict, only these electron beams will pass through them, and the electron beams which are coming from here, it will not pass through. These are all blocked. If this is your, I'll make it much more clearer. Sorry for this hodgepodge. Apertures are the physical holes present. So if this hole I have selected and the electron beams are coming, these all will be traveling a straight path. So in this case, only these three rays will pass from this aperture, and the remaining, the extreme right and extreme left rays won't pass from this aperture. So this aperture blocks certain these certain rays which are far away from the optic axis. This aperture is aligned, this center one, no, which I am elongating right now, is basically the ray which is just along the optic axis, and as we go from here to here, the distance of the ray from the optic axis is being increased, and later on we'll study as the distance of the ray of electron ray far away from the optic axis, the more will be the aberrations. So the aberrations will always distort the image. So our main aim is to have the rays which will not distort the image, the information provided by the image. So we will try to have the rays which are very near to this optic axis, and we will try to block the rays which are far away from optic axis. Also, this alpha value will depend upon the resolution, the current, the depth of focus. We discussed this depth of focus very in very detail in the optic axis, so I won't repeat that thing over here now, because we all know what this depth of focus means. And then I need to tell you the why this alpha will affect the image. So this alpha will optimize the resolution. Alpha, as I told you, is the convergence angle. It will also control the current which is carried by the electron beam. It will also relate to the depth of focus of the image. So this thing you need to keep in mind, that smaller alpha increases depth of focus. Depth of focus but decreases beam current and affects the lens aberration. Smaller alpha means I have these two beams. These both are at, this is my specimen. These both initiate from here, same point only. In this case, my convergence angle is this, and in this case, my convergence angle is this. So in case A and in case B. So in case A, I have smaller alpha. This smaller alpha will means that I will have a high depth of focus in the image. That means if I have a very rough surface area like this, then I'll be able to see both this thing and this thing in focus. While in the case of B, where the alpha is very high, I can only focus either point this or point this, because at higher alpha the depth of field is very small. But there is another thing which you need to keep in mind, that when you have this smaller alpha, though it will increase the depth of focus, but it will decrease the beam current and it will affect the aberrations. The current value will decrease the resolution. So as a result, in the case A, the depth of focus D, I'll denote it as DOF. So where alpha is smaller, the depth of focus is very high, the current, that is I, is very low, and as a result the resolution, I will write it as RES, the resolution will also be low. So depending upon the information you required, like if your specimen is this rough, then you need to require higher depth of field, depth of focus, so you require lower alpha. But if your sample is much smoother like this and you want to study this specimen much more clearly, then you need to get high resolution. So in that case you will follow this B, case B, where you will have a higher alpha. I think I have made myself very clear over here. Is there any doubt? Then let me know. I guess no doubts are there, everything is quite clear. I'll move to next slide. Sorry. So here we have the spherical aberrations, the chromatic aberrations, the astigmatism, and the diffraction. The spherical aberration will be due to the lenses, where the rays which are far away from, if this is your optic axis, I'll just draw that optic axis so that it's clear to you. The marked red one is the optic axis. So the rays which are far away from the optic axis converges at a certain point, and the rays which were very near to the optic axis will focus at certain point. So this will be the plane of least confusion. This is the plane in between the two focused points. So the image will have the spherical aberration, and the contribution of this spherical aberration is given by half cs alpha cube, and this spherical aberration is directly proportional to alpha cube term. These things are being used to calculate the aberrations present in your image. So due to the spherical aberration, your alpha cube will contribute. So as the alpha will increase, the spherical aberration will increase. So because alpha will increase, that means the far away regions are coming, rays are coming. So it will always increase your aberration. So to reduce the spherical aberration, we will try to reduce the convergence angle, that is alpha. But we have this diffraction limitation. This diffraction limitation will always be present in the system. This diffraction, the last one, this diffraction you can never remove, never ever remove from your image. This will always be present in your image. Here also the diffraction limitation is there, where the diffraction limitation given by the dd is given by 0.61 lambda by alpha. So this diffraction limitation is inversely proportional to alpha. So this says that to decrease the diffraction limitation, you should have a higher alpha. So when the spherical aberration and the diffraction are being considered, and we plot the graph to have the optimum alpha value, firstly we have this diffraction limitation, which is related to 1 by alpha, proportional to 1 by alpha, and also we have this spherical aberration limitations, which is proportional to alpha cube. So by combining these two, we should have the alpha in this range, we should have the optimum value, so that we can have the minimum lens aberration and good quality image. This diffraction you can never remove from your system. These you can correct as much as there is the capability of you, your instrument, and everything. Then we have this chromatic aberrations, where the chromatic means that different wavelengths of light will be focused at different point. This we also discussed in the optical microscopy, where we saw that in the white light the blue rays will be focused at a different point as compared to the red rays. As a result, the image which will have which will obtain will have the colored fringes just around the exact image. So that is given by dc is equal to delta e by e cc, that is the chromatic aberration term, into alpha. So this is also directly related to the alpha. And later we have this astigmatism. This also we discussed in the optical microscopy, where the two rays which are coming perpendicular will get focused at different point, like these two rays which are longitudinal will focused at different point, and these two rays will get focused at different point. So this will cause the dragging in the image, and this is known as the astigmatism. So these all are the lens aberrations. So our aim is to correct these lens aberrations to get a very high resolution image of the object. But please keep in mind that this diffraction limitation will always be present in your system. How good, how bestest system you can have, but this diffraction is the basic limitation in the system. These lens aberrations are most important for the basically for the objective lens. Can anybody tell me where is the objective lens being placed in the SEM chamber? We discussed this in the previous slides. Can anybody tell me where is this objective lens being placed? Anyone? Yeah. Okay, very good. Yeah, so if we'll combine all the astigmatism and everything, all the lens separations, then the diameter of the probe, that is D probe, will be given by the under root of dg square, that is the Gaussian diameter of the probe, and the chromatic diameter square, the spherical aberration diameter square, and the diameter of the diffraction limitation square, and wholes under root. So this is given by D probe square is given by 4 IP divided by beta pi square, plus then we'll consider this chromatic aberration followed by the spherical and the diffraction limitation. This is inversely related to 1 by lambda. So this one will be which aberration? This one will be diffraction one, and this one is the spherical aberration, which is given by 1 by 2 CS alpha cube. So we have squared whole the term. Then we had the chromatic aberration, which was given by delta E by E CS into alpha. So the size of the probe, that is the D probe. D probe is basically the diameter of the probe. So the probe size will depend upon the beam current, this using this one, the divergence, the wavelength, the energy, or the aberration, and the aberration coefficients, this CS, CC, and everything. This is basically CC. This one I need to correct it. This is chromatic. Okay. Then we will discuss briefly about the parameters which will govern the formation of the image. The first one is the probe size. I have discussed this many a times that depending upon the probe size you will have the resolution. Smaller the probe size, higher will be the resolution. Smaller the probe size, lower will be the brightness. If I need to explain this to you, then it will go like, sorry, if this is your specimen and you have a probe which is this, and another you have probe which is this. So this A1, first one, has a smaller probe size. The smaller the probe size, the higher will be the resolution, because this probe will detect the another feature which is present over here, but this probe, which is very big in size, will not be able to detect this feature which is present here, because it will directly go to the next region. So the smaller the probe size, the higher will be the resolution. And the second point is that the smaller the probe size, the lower will be the brightness. But we need higher brightness for a good quality image. So we always need to compromise on certain things, and depending upon the information required, we will change the orientation or the things which in the SEM chamber. Then the probe current and the brightness. The image requires larger current. As I told you, larger current means larger brightness, because brightness is directly related to the current, as we saw in the previous slides, that brightness beta is given by 4IB divided by lambda square d square alpha square. And then this convergence angle alpha. Convergence angle is given by this alpha. This convergence angle unit is steradians. So this we have already discussed, that as alpha decreases, the depth of field will increase. We have already discussed in the previous slide. I guess we discussed here. Yeah, that thing is not there, but we discussed it, that the depth of field will increase if the alpha will decrease. And if the alpha is decreasing, then the aberrations will also be decreased. The brightness will also be decreased. So I told you that brightness will decrease, that means the current will decrease. That will decrease, that means the resolution will be poorer. So if you need to have a higher depth of field, then you need to compromise the resolution of the image. So depending upon the information you require, you can vary your convergence angle and everything. The probe size dp is the diameter of the beam which falls on the specimen, which I have already told you. This brightness is beta, which is the current density divided by the solid angle. And this probe convergence angle alpha is the angle made by the cone of electrons with the central axis. Central axis means the optic axis at the sample surface. Then we have this brightness which is determined by the gun. We can't change the brightness. The brightness always and always remain constant from initial to the specimen. From initial start, from the gun source only it will change, and after it is being emitted from the gun source, the brightness of the electron beam will always be constant throughout the chamber until and unless it will reach the specimen. So this brightness always remains a constant value in whole the chamber. So we are interested in small spot size. So to know about the small spot size, which will be given by the diameter, so we will rearrange this. Then we can get this pi square and alpha square will go above, and this 4IB will go down, and then this will be 1 by d, and then we will just reverse it, and then we will get d diameter of the probe as under root of 4IB divided by beta pi square alpha square. Also, when we are when we need to calculate the current, we need to have, basically we have already discussed that to get a high resolution, we need to get a smaller spot size, that is the d Gaussian should be smaller, but we require for a good image quality that the probe current should be high. So by rearranging this above brightness equation, we got the probe current I probe as beta pi square alpha square d square by 4. So according to this, alpha should be smaller, and the smaller spot size means alpha should be larger, and higher the current, alpha should be larger. So according to these two, alpha should be larger. but alpha also affects the lens aberrations, hence it will limit the spot size. So depending upon these two, you can't say that you can have the maximum alpha as much as you want, because it will have the more lens aberrations as alpha will increase, because the spherical aberration depends directly on the alpha cube term, which we discussed in this slide. So we can't blindly increase the alpha by looking at just these two, the diameter of the spot size and the current. So if we will increase the alpha blindly, it will cause a very huge lens aberrations, mostly the spherical aberrations. So we need to have the optimum value of alpha to get the best image quality. Also, we did discussed in the previous slide that the diameter of probe is the combination of all the aberrations present in the system, where by rearranging all these terms we can have this optimum alpha value given by dp by cs whole raised to power 1 by 3, and the d minimum will be given by this value, and the I maximum, that is the maximum current we could obtain, will be given by this equation. So we always need to compromise on the on various things, and depending upon the information we will have different compromisation. So I also there is one more point which you need to keep in mind, that the can astigmatism can be completely removed, but spherical, chromatic and diffraction aberrations cannot be completely removed from the system. This chromatic also you can remove when you are using your monochromatic source, but this diffraction, how good, how bestest system you have, you won't be able to remove this astigmatism you can completely remove just by having your different combinations of your stigmator coils. Then there are certain other conditions which you things which you need to keep in mind, that the electron beam which is traveling in the SEM chamber. So what does the things which are affecting the electron beam voltage? So electron beam, generally the energy of electron beam is given in kilovolt, kV. We can also mention it is in K electron volt. Electron volt is the unit of energy. V is the unit of volt. You all know V is volt. It is not energy. But every time when you will see that this SEM is operated at 5 kV, this SEM machine is operating at 10 kV, 15 kV. So they always mention the unit of electron volt energy as kV only. So there these things are being interconverted, like the energy of electron is given in kilovolt only. So ideally it is in kilo electron volt, because electron volt is the unit of energy. So I need to, so what we were discussing, yeah, so the effect of beam voltage. So as we increase the beam voltage, the wavelength will decrease. As the voltage will increase, suppose this is your specimen and your electron beam is coming from here, it will have certain interaction with the specimen. So if you will have high voltage, it will have high current and it will have lower D value, that means lower probe size. So ideally previously we were able to, we concluded that higher kV will solve all the SEM problems, but the higher the current, higher will be the spherical aberrations. So we need to have a short focal length, the better lens design. So now everyone is moving to the lower kV, that is, now if you are using 5 kV 5 kV source, now 5 kV source. Now people are trying to move to lower kV to have a better image quality. Earlier people were thinking that higher the kV, higher will be the image quality, but this spherical aberration also contributes to the image. So the image which were taken at very higher, like 20, 15 kVs, they were very low quality, low resolution images were being obtained. So depending upon all these conditions, the SEM should be optimized in such a way to have a best resolution of your image. Note, in the limit of no beam current. That means, so if we need to have the smallest spherical aberration, that means we need to have the smallest current, and the smallest current ideally I won't say, sorry, so the theoretically the smallest current will be the zero current. So then d minimum will be given by cs to power 1 by 4 lambda to power 3 by 4. But this probe current 0, that means no probe, no electron is being fallen on the sample. But theoretically, if this is 0, then the minimum, that is a minimest diameter of the electron probe will be given by this equation: Cs, spherical aberration to the power 1 by 4, and lambda, that is wavelength to the power 3 by 4. This is basically the theoretical limitation for the smallest probe size in the SEM. Then I would like to discuss about, till now, if I see the basic ray diagram, till now we have seen this electron gun and how these condenser lenses and all contributes the apertures, the aberrations from the condensers and the objective lens, how they affect the electron beam. Now the specimen will interact with the electron beam, and then it will emit different radiations. So now we will study the interaction of the electron beam with the specimen. So this one is the incident electron beam. This, when falls on the specimen, will produce various different kind of signals, like certain amount of electrons will be absorbed by the specimen, and it certain will generate the electron hole pair. It will also generate the reflected back one will be the Auger electrons, the backscatter secondary electrons, the secondary electrons, the characteristic X-rays, the visible light, and the rays which are being transmitted from the specimen will include firstly the direct beam with the maximum intensity, and then the elastic scattering electrons, the inelastic secondary electrons, and the Bremsstrahlung electrons. These elastic, inelastic, Bremsstrahlung, visible, characteristic, secondary, backscattered Auger, all these electrons will be produced by the specimen always, all the time. And depending upon the detector which you are using, you will get information based on the type of detector which you are using. You can't control the rays which are coming out from the specimen, because every time the electron interacts with the specimen, it will produce all these kind of signals. But depending upon the detector which you are using, you can have different kinds of images. So first we will discuss about the elastic scattering. So the basic things which we know from our childhood is that the elastic scattering is the one scattering where the energy is not being lost, all the energy is being intact. Like if you are hitting a ball, for example, if you are hitting a ball on the ground with a certain force, it won't return back to the same force to you. You need to, the next time the ball comes up, you need to apply certain force again to have the same motion of the ball. That means the ball is reducing, ball is, the energy which you are providing to the ball is getting degraded. So that is the inelastic thing. The elastic thing will be the one where you hit the ball, like there is one small plastic ball and you hit it to some at certain angle to a wall, and it will reflect back at a certain angle, specific reflected angle from the wall. Then it will have a slightly lesser energy, but more or less it will have a similar kind of energy. If this is your wall and we have pushed your ball here, it will go in this direction. So this is where the no energy is being lost is known as the elastic scattering, whereas the scattering where the energy is being lost but the direction remains the same is known as the inelastic scattering. In elastic scattering, I'll just repeat it. In elastic scattering, the energy remains the same but the angle changes. The direction of the motion changes. And in inelastic scattering, the direction of the motion remains the same while the energy of the system decreases. So, I'll discuss about the elastic scattering first. So, in elastic scattering, electrons are scattered by the atomic nucleus of the sample, partially screened by the bounded electrons. So, in the elastic scattering, the direction will always be changed. So, it occurs from angle of 0 degree to 180 degree. And in inelastic scattering, the energy transfer from energy is always decreased but the direction is always the same. So the energy is transferred from the beam electron to the electron of the specimen, or to generate which are or could it could be used for the generation of these photons or phonons. It can also have the lattice vibrations. It can give energy to the inner shell electron or to outer shell electron. So there will be a complete range of energy transfer between the single inelastic event. So this can have multiple region multiple so there will be multi a big range in which the value of the electrons will be present. Here the value of electron energy will be the same only, but in the inelastic case the energy of electron will vary very much. Then I'll discuss about the secondary electrons and the backscattered electrons. The secondary electrons are the ones which get excited of the which are basically the excitation of conduction electrons, which will lead to the secondary electrons. These secondary electrons are the low energy electrons. These are very loosely bound electrons which are present in the conduction band of the system. These basically, this is very raw definition, but it is always being used from very long back, that the secondary electrons will be the one which will have the energy from 0 electron volt to 50 electron volts, and mostly they will have energy very less than 5 electron volt, because they are very loosely, they are due to the electrons which are loosely bound to the system. Then we have this backscattered electrons. Backscattered electrons will have an energy greater than 50 electron volts. So this back secondary electrons energy will be dependent upon the atomic number. So higher the atomic number of the system of your specimen, higher will be the back secondary electron. So if I need to ask you people that if I have a atom A which is having a higher atomic number and I have a atom B which is a lower atomic number. So the higher atomic number atom A will have higher back secondary electron. So the detector will detect more number of back secondary electron. So when we will see the image, it should seem more brighter or less brighter. It should have a higher contrast or lower contrast? Can anybody have a certain guess based on the things which we are discussing? The atom which is having a higher atomic number will be should be brighter or should be darker as compared to the lower atomic number. Yeah, because more number of electrons are being emitted, so it will be much more brighter as compared to the lower atomic number one. And the last point in this is that this back secondary electrons, higher the atomic number, higher will be the back secondary electron, and it will be much more brighter, and it directly correlates to the atomic number. So if you want to know about the atomic number of your specimen, you can collect the back secondary electron. But if you want to know about the topology means the surface of the specimen, then you need to collect your secondary electrons. These secondary electrons will tell you about the specimen surface area, and the back secondary electron will tell you about majorly about the atomic number. Then lastly I will discuss about the effect of condenser lens strength and the working distance, and then we will move towards the assignments. So here I have two cases. Firstly, the weak condenser lens and the strong condenser lens. So this is our condenser lens. So this is in the case A, it is a weak condenser lens. So the weak condenser lens will focus at a higher distance as compared to the strong condenser lens. The stronger the lens, the more near will be the focal point, and it will focus at a smaller distance with the lens. So in the weak condenser lens, firstly we'll discuss this one. So weaker the condenser lens, it will get focused at a higher point, and as a result you will have this kind of aperture over here, and then this will be emitted out, and then you will get the convergent probe which will be like this. And in this case where you have a stronger condenser lens, so here you have this diameter of the probe as d1, and then this has a very high alpha value. This is basically the alpha 1, because it is converged at a very lower point, smaller distance, so it will have a larger alpha. So at larger alpha, so when this aperture is being present, it will get focused at the specimen. So the specimen position is same, it's just the basic difference of the condenser lens strength. So here you can see that the probe size is much higher as compared to the case 2. So you can say from these two diagrams that in the strong condenser lens, the probe size will be much smaller. So the probe size is smaller, the resolution will be high when we have a high condenser strength lens as compared to the weak condenser lenses. Next we will lastly we'll discuss about this working distance. What will the effect of this working distance? So here the condenser lens, this is the electron gun, and the electrons beam is coming from condenser electron gun to the condenser lens. This condenser lens strengths are same. So this d1, which is the diameter of the electron probe after the passing through the condenser lens, is same, and after passing through the objective lens, it get focused at a certain point. So when the working distance is increased, the sample is basically working distance is the distance of the objective lens to the specimen. So this q2, which you can see here, that is the distance from the specimen top to the objective lens, is basically given as the known as the working distance. So here the working distance is increased, the probe size is increased. So as we increase the probe size, this alpha is decreased. So as a result, the resolution will decrease, but the depth of focus will always be increased. So you need to know when you need to have a lower working distance, if you want to have higher resolution. But if you want to have higher depth of focus, then you need to have a larger working distance. I hope I have made myself quite clear in the introduction of this SEM part. If there are any doubts, do let me know. Otherwise, we will discuss about the assignment and quiz of this week. If no, everything is clear. Okay, I doesn't, no hand is being raised. Then I'll move towards the quiz part. So this is the practice part for the week 4, where the first question, I'll just select the pointer, where the first question says the portion of electron gun that leaves the gun through the hole in the anode is called which type of current? Beam current, emitted current, probe current. Now I want your contribution to answer these questions. I have explained each and everything to you which are being asked in these questions. So are you all with me? If you have all understood the concepts which I have taught you, then we should together do these questions. Just give it a guess, then we will discuss the portion of electrons that the portion of electron, someone have mentioned something, probe current Neha is saying. Does everybody agrees with her? That leaves the gun through the hole in the anode. Probe current, I told you, is the current which is feel which is being feel, felt by the specimen. The current which is being passed through the anode is known as this beam current. Option A. The probe current is the one which is experienced by the specimen. They are asking about the after the anode. It is known as the beam current. So this is clear, Neha? Okay. Shomya is saying beam current. Yeah. Okay, Neha. We'll move towards the question 2, which says in an electromagnetic lens, the magnetic field exerts force on a moving electron in a direction perpendicular to the direction of field, perpendicular to the direction of propagation of electron, parallel to the direction of propagation of electron, perpendicular to both direction of field and the direction of propagation of electron. So the electron was moving vertically downwards and it was feeling a force. The force was exerted in this direction as well as in this direction. So this is perpendicular to both the direction of field and the direction of propagation of electron. So here option D is the correct option, which we discussed in the initial slides only, that if the electron is coming in this and the magnetic field is in this direction, this is the direction of magnetic field B, this is the velocity of electron. It experienced first a force in this direction, then it experienced a force in this direction. So this experience a force which is perpendicular to both the direction of field and the direction of propagation of electron. As a result, it follows this spiral kind of path, and as the beam converges, it also converges. So option D is the correct answer. The question number 3 says that the space charge effect is minimum when dash is used. So the space charge effect is minimum when high voltage and low beam current will be used. This you need to keep in mind, that when high voltage and low beam current is used, then the space charge effect will be minimum. So question number 4 says that the crystal structure and grain orientation of the specimen are obtained from dash signal. The crystal structure and grain orientation. the grain orientation and crystal structure. These two should be obtained crystal structure. Secondary electron is used for the topography information. The back secondary electron. Here option B is the correct answer. So the back secondary electron is being used for the grain boundary and the crystal structure detection. The question number last question says that the increase in working distance, this we discussed in the last slide only. Can anybody tell me? Increase in working distance leads to dash spot size and dash the image resolution. This we discussed in the last discussion slide only. Option C. Option C, which says larger and degrades. Yes. So if we increase the working distance, the spot size will be larger and the image resolution will be smaller. So the image resolution will be degraded. Abhishek Sahu, do you have any doubt? What second question? Second question. You said radially and you said radially and perpendicular. Yeah, so option D is correct, which I explained you know. This one. Okay, radially I means in this direction and perpendicular to the magnetic field that means in this direction. No, 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 no. This is the motion of electron. This is the velocity of electron. The magnetic field is being provided in this direction. This magnetic field has both vectors. This magnetic field has radial vector as well as this vector, which I told you in the initial slide only. I'll just go to that slide and I'll. Radial one is this one. This is longitudinal one and this is radial one. Radial and perpendicular are different things that I am not denying. Here they have asked that the magnetic field exerts a force on moving electron in a direction. So if your electron is moving in this direction, so the force, firstly the force due to these things, the motion of electron and the magnetic field, the force is exerted in this direction and then the force is exerted in inside the plane of the screen. So that means which is perpendicular to both the direction of field and the direction of propagation of electrons. Okay. Have I made myself clear now? Okay. Now we'll move towards the assignment quiz of this week, which says what type of signal will be used to get the maximum contrast. Maximum contrast means we already discussed. Can anybody please make a guess? Using this secondary electron, back secondary electron, X-rays, visible light, transmitted electrons, which will have the maximum contrast. The contrast is mostly always given by the Z, back secondary electrons. So here option B is the correct answer. The second question says a polymeric and a powder sample properly coated operating at 20 kV is extensively charging during a secondary electron focusing. How the operator can take proper imaging. So your sample will be charged. For example, this is your specimen and your electron probe is coming in this direction. Electrons are always negatively charged. So if you don't have conducting medium for the electrons to go, the electrons may accumulate on the surface of the specimen and it will generate a negatively charged surface. So in your image, your this region will appear very bright, white kind of thing, because your electrons are being accumulated here. So you should always have a conducting path of the electrons so that the electrons should not get accumulated on the surface of the specimen. So in the polymeric or so the question says a polymeric or a powder sample properly coated operating at 220 kV is being charged due to secondary electron focusing. How the operator can take proper image? So the operator either should reduce the kV EHT value, the operator should change the operating mode, or the sample can't be imaged. So here the operator should reduce the energy of the electrons, because the energy of electrons are too high that they are being accumulated on this surface and they are giving this bright image which is known as the charged image. So the operator can reduce the EHT value to get a good quality image. The next question says, question number 3, a fractured sample micrograph is shown in the figure. This one. What kind of signal was used for analyzing the specimen? Can anybody make a guess? Since we have been discussing it from a very long time, just by looking at this image, can anybody make a guess which type of electrons are being used to image this specimen? Secondary electrons or backscattered electrons or ion beams or visible light? Since you can see that there are a lot of regions, this is not a smooth surface and there are regions which are very above and very below. So this is having a very good depth of focus image. So now can you please tell which type of electrons are being used to image this? Please try. Anyone? No one is willing to answer this question. We discussed secondary electrons is used for the topographical information. The back secondary electrons are used for the Z contrast imaging. So here you can see that there is a very good topographical information is being obtained using this image. So here you have used secondary electrons to image this specimen. The next question says the figure shows the contrast for gallium nitride chip in a mixture of light emitting diode East cramp. What type of signal was used for this? So this you can see is the gallium nitride. This is appearing much brighter as compared to the rest of the image. So now here can anybody make a guess after this third question? This fourth question is much very easy. Can anybody tell which electrons are being used in this question 4 to image this gallium nitride? Option B. Option B, yeah, back secondary electrons. Who is this? Myself. Rajesh, okay. Yeah, please try to answer these questions. These are just for the practice. We have discussed all the concepts and everything in the previous slides. So here option B, that is back secondary electrons, because this gallium nitride chip is appearing much brighter as compared to the rest of the thing, though this chip and the other chips all have different orientations and they all have different here you can also see that the depth of focus is also very bad. Which of the following is true for the following interaction volumes? Here we have two interaction volumes. The first one is having a very low interaction volume and the second one have a very high interaction volume. So A corresponds to high accelerating voltage or B corresponds to high accelerating voltage. I need to tell you one thing here. Then when I discussed that if we increase the accelerating voltage, if we have a higher accelerating voltage, it will go much deeper into the specimen, and the lower the accelerating voltage, it will be very near the edge of the specimen only. But if we will have a higher voltage, it will go much deeper into the specimen. So now, which of the following is true? So option B will correspond to higher accelerating voltage, since it's have a higher interaction volume. This I will discuss in the next lecture. We didn't have enough time to discuss this in this lecture. So this basically, the electron beams when falls on the specimen, it will interact with the specimen, and this interaction is given by this interaction volume. It is basically this pear shaped volume of the specimen, which is known as the interaction volume, from where all the electrons are being emitted, which we can detect. So this is basically the interaction volume, and depending upon the accelerating voltage, higher the accelerating voltage, higher will be the accelerating, oh, higher will be the interaction volume. The question number 6 says interaction volume increases with increasing atomic number and decreases with increasing atomic number. I guess there is a problem in this question. Both the things are saying with increasing atomic number and with increasing atomic number. So the first statement, so I will discuss with this only. Interaction volume increases with increasing atomic number. If you have a higher atomic number, you will have a lower interaction volume. Lower interaction volume means why? Because when you have a higher Z means higher atomic number. So if you have an element with a higher atomic number, it will have higher electrons. Higher the electrons, higher will be the repulsion of the incoming electron to the electrons of this atom itself. So if this is at higher atomic number, it will have higher electron, so it will repel the electron beam. So as a result, the electron volume, interaction volume will be smaller. So in this case, the interaction volume increases with increasing atomic number. So using this statement is false, but the second statement is true. So there is a problem in this question, but you just need to understand the concept. The seventh question says that on what factor does the intensity of secondary electron depends upon? Secondary electron depends upon the shape of irradiated object, the chemical composition of the irradiated object, the number of electrons ejected, the size, chemical composition. Have anybody commented anything? Oh, something was wrong. Okay. So the intensity of secondary electron depends upon what factors? The last option says that the size and chemical composition of the irradiated object, number of electron ejected, and on the number of electrons reabsorbed by the surrounding. All these things will affect the intensity of secondary electron. The size, the chemical composition, the number of electron ejected, the number of electron reabsorbed by the surrounding. So here option D is the correct answer. The secondary electrons are useful for microstructural study in SEM, while back secondary electrons are useful only for diffraction study such as EBSD. If this only word was not have been there, then this statement must have been true. But they have mentioned this only. So according to me, if they are saying that this first statement is correct, that secondary electrons are useful for microstructure study in SEM, while the back secondary electrons are useful only for diffraction study in such as EBSD, The secondary electron are also used for the contrast imaging as well. So according to me, this statement is false. So option B will be the correct answer for this case. The second last question says that the secondary electron generated from more than 2 nanometer depth cannot emerge out from the specimen. This interaction volume which we have showed in this are much more than this 2 nanometer. So this statement is incorrect. The secondary electron generated from more than 2 nanometer depth cannot be emerged out. No, they can be emerged out. So this statement is a false statement. And the last question says that the depth of field of scanning electron microscope will increase. This you people will tell me the answer of this question. This we have discussed multiple times in our today's lecture. The depth of field of scanning electron microscope, the depth of field will increase by objective aperture diameter increasing, by increasing the magnification, by increasing the working distance, or none of the above. I want this answer from you people. Any raise hand? Anyone want to answer? How we will the depth of how will the depth of field will be increased? Option C. By increasing the working distance. Yeah. So by increasing the working distance, though the yes, Ramu, the answer is option C, by increasing the working distance. So as we increase the working distance, we have seen multiple times in multiple slides in multiple ways that as we increase the working distance, the alpha will change. As a result, the depth of field will increase and the resolution will decrease. So I guess I have made myself much clearer as much as I could have to give you the basic introduction of this SEM course. If there are still any doubts, any questions, any queries on any topic or any question of the assignment, do let me know. All these questions are clear to you, or do you still have any doubts? From sixth one more explanation now. Question number 6. That question itself is not correct. That question says both the statements. I guess there is some misprinting error in that question. Yeah. Just because they are saying that the interaction volume increases with increasing atomic number, the interaction volume decreases with increased atomic number. The second statement is correct. It decreases with increased atomic number because I told you that suppose if this is your specimen, this have a higher, suppose I'll just draw it to make it more clearer to you. Sorry. Yeah. If this is your atom which is having a higher atomic number means higher number of electrons in the outer shell, right? So higher atomic number means higher electrons. So higher will be the repulsion of this atom to the incoming electron beam. So it will repel more to the electron beam the higher the atomic number. So this interaction volume which I have shown you in this option, in this question number 5. So this is basically the interaction volume. So if the specimen A is having a higher atomic number, it will have a higher number of electrons. It will repel the incoming electron beam much more as compared to the lower atomic number. As a result, it will have a lower interaction volume. So now you can consider this that the specimen A has a higher atomic number. So as a result, it have a lower interaction volume. Whereas the specimen B have the lower atomic number. Lower atomic number means low number of electrons. Low number of electron means there is less repulsion between the electrons of the atom and the incoming electron beam. As a result, the interaction volume will be much higher in the lower atomic number case. So this is low Z and the A1 is high Z. Got it? Okay. Okay. Um, you can say the statement is false because it is saying both the things only. There was, I guess, there is some misprinting. Otherwise, there is no means. No, they have asked with respect to the atomic number only both the times. It cannot be anyways true that it will increase and decrease with atomic number. So this statement is itself a problem. Okay. Any other doubts? Okay. Any other doubts? Thank you, Suresh.